Hello and welcome to a video on composite functions. Now this is part 2 of composite functions. It assumes that you already have a foundation understanding what a composite function is, but we're going to look at 3 different things in this video. And the first one is a focus on the domain of the composite functions. The second topic will be a focus on how to use composite functions to test to see if two functions are inverses of each other. And then the third will be to take a composite function that's already composed and pull the pieces apart, which is called finding the components of a composite function. Okay, so the first thing that I want to do is I just want to think about a function. Let's just say f of g of x. Now g of x is the inner function and f of x is the outer function. And there's 2 things that go into defining or determining what can be defined for the function. And the first thing is whatever the input is. Now x is the input. The input has to be defined for the inner function. So that's the first requirement. Now remember how composite functions work. You put something into the inner function, you get an output. The output of the inner function becomes the input of the outer function. So the second restriction on the domain is that the output of the inner function has to be defined for the outer function. Okay, so let's look at this now in the context of 2 functions, f and g. So we're looking at f circle g first. So f circle g, remember that means f of g of x. And in this case, that means that the input for f is the entire function g of x. So this would be saying what we're really looking for here is f of g of x, right? This, which is 4 over x minus 1. And that means we're going to rewrite f of x, but we're going to replace, I really should make this all red here, we're going to replace our x right here with that input 4 over x minus 1. It's a little bit weird the first couple times you do it like this, but we looked at this in the first part of composite functions. All right, so we're going to rewrite f of x. So we have 1 over, and this is the spot where we get x, right? Right down here is where we get x, and then it's going to be plus 2. But remember, x is now 4 over x minus 1, so that's what we're going to put in there, 4 over x minus 1. All right, now let's take a look. This is our function f circle g. This is f circle g. And I'm just going interchangeably between this form and this form. Remember that they mean the same thing. Okay, so one way of looking at this, and the way I kind of like looking at this, is you're looking at a complex fraction, and there's 2 fraction bars. In other words, there's 2 denominators. And we know that one of the main restrictions on domain is making sure that those denominators are never equal to 0. And that pretty much says it all. That's going to be our process. So the first denominator is this simple one right here, and we know, number 1, we know that x minus 1 cannot be 0. The second denominator is the whole thing, this entire thing here, all of that, and so we know for number 2 that that whole denominator, 4 over x minus 1 plus 2, also cannot equal 0. All right, now looking at it in these 2 ways, that's a perfectly good approach, but I just want to kind of talk for a minute on how this number 2 is the same as number 2 right here. So this would be saying that the output, whatever comes out of this 4 over x minus 1, it just can't be negative 2, because if it's negative 2, that would not be defined for the outer function, right? X cannot be negative 2, so the output of 4 over x minus 1 can't be negative 2. But in practice, you can just solve these 2 equations and you have your 2 exclusions, and that's what we're going to do. All right, so the first one, pretty straightforward. Just add 1 to both sides, and we know that this means that x cannot be positive 1. And we're done with that one. That one's pretty simple. This one, we're going to start out by subtracting 2 from both sides, so we know that 4 over x minus 1 cannot equal negative 2. And we're just going to solve this as if it were an equal sign instead of a not equal sign. So it's not that different. So we have 4 cannot equal negative 2 times x minus 1. In other words, 4 cannot equal negative 2x plus 2. Subtract 2 from both sides, and we get, here we'll just put a little error here, we'll get 2 cannot equal negative 2x, or dividing by negative 2, we now know that x cannot equal -1. So our domain for this composite function is all real numbers except x cannot equal 1 or -2. -1, sorry. So that's one way of saying it. The other way of saying it is an interval notation from -infinity to -1, unioned with -1 to 1, and then unioned with 1 to infinity. That's just an alternative way of saying the exact same thing. Now, another way of doing the same problem would be to take that simple exclusion from exclusion number 1, focusing on the inner function, and saying, well, I can tell right off the bat x can't be 1, because that would mean the inner function is not even defined. And then simplifying the composite functions. So we're going to simplify this whole function and then just get the domain out of that. And that's going to actually give us our second exclusion, which we worked to get right here. It's just an alternative way of doing it. So we're going to simplify this whole thing, and you guys can try it. Okay, there's our composite function simplified. And now we can just look at the domain restriction from that, which would be to look at the denominator and say we know for this to be anything meaningful, we know that 2 plus 2x couldn't possibly be 0. In other words, subtract 2, divide by 2, and you get x could not possibly be -1. And that's what we found using the other method too. So the bonus, the advantage of option 2 is that while you're getting that second part of the domain, the one that's a little bit harder to find, the exclusion that's harder to find, you're also getting the composite function done. So it's like getting two things done at once. All right, so what I'd like you to do now is that we found f circle G. Why don't you try to find the domain of G circle F? The domain of G circle F. Okay, so there we go. We just replaced x with 1 over x plus 2 and found the two restrictions from the two denominators. Okay, I kind of skipped a step here for my second restriction. I know that 1 over x plus 2 can't equal positive 1, so I just started out with that. I could have said 1 over x plus 2 minus 1 cannot equal 0, but I knew that would reach the point where I'm adding 1 to both sides. Now, just a word of warning here. If we look at our two functions, here's what not to do. Don't look at the two denominators and say, well, one of the denominators is can't have a -2 and the other can't have a 1. So therefore, the domain would just be all real numbers except x cannot be, well, -2 or positive 1. Don't ever do that. That's not how it works. It's just not that simple. And if you look at either direction that we got here, the exclusions were -2 and -1, or positive 1 and -1. They were never -2 and 1. So that will almost always get you the wrong answer. Okay, let's look at example 2. Now, example 2 is pretty much a review of just finding composites, with the point that when you find composites and they're equal to each other and they're both equal to x, you've got inverses. So if we're looking at two functions, f and g, and we want to know whether or not they're inverses, we take the composites of both, and that's the composite test. Okay, so let's go ahead and start out. We're going to have to do both. So we're going to find f of g of x, and we're going to find g of f of x. And we're going to hope that they're both equal to x. And that's a question mark so far because we have to show it. But if we have functions and we're trying to confirm that they're inverses of each other, this is the way to do it. Okay, let's first find f of g of x. Okay, just to make sure you're on the right track with the first step, here is the function f of x, right? F of x is -2x plus 1. And this input right here, this is g of x. And then here's the function g of x. G of x is -1/2 x minus 1. Looks like I didn't quite close a parenthesis there. Let me just close that parenthesis. And this part right here, that's f of x. So f of x and g of x become the inputs. Now let's simplify each one of these. Okay, now there's many ways you might have simplified these, but they should always end up in the same place, and that is both of these composite functions are equal to x. In other words, what we found here was that f of g of x was equal to g of f of x. I did the same thing twice. G of f of x, they're equal to each other because they're both equal to the same thing. They're both equal to x. And therefore, f and g are inverses. Okay, one more type of problem here. Let's find the components of a composite function. So now we're looking at a function that we're told is already a composite function. So h is already a composite of two functions. And we just want to find functions that would make sense here. Now, I put a note here that there's more than one answer possible, and that's kind of important to keep in mind. But we want to try to be as close as we can to something that resembles what we do with the parent function. So with the parent functions, what I would say is that the inner function here would be x minus 5. So that inner function is g. So I'm going to just start out saying g of x is x minus 5. Now, is it the only way? No. You don't have to do that. You could say it's x minus 5 squared. But I'm going to go with x minus 5. And therefore, that has to go inside of the outer function which is f. And that would have to be the 3 over that thing squared. Now, just to check it, these are our components. That's it. We're done. Except just to check it, let's make sure that f of g is in fact what it's supposed to be. So f of g would be f of x minus 5, which means we're going to put x minus 5 into the we can put the x minus 5 into the f function, which is 3 over that squared. So this is going to be 3 over x minus 5 squared, and that is in fact h of x. So we've got the two components of h of x. Okay. Another way you could have done it, you could have made the inner function x minus 5 squared, and the outer function would be 3 over x, just in case anybody came up with that. So here we'll put an alternative, would be that the inner function, which is g, could have been x minus 5 squared. In that case, the outer function f would be 3 over x. Now, if you compose these two, this is an alternative. If you compose these two, you're going to get 3 over, because that's the inner function goes here. So this whole thing would come down here, and you would have the same thing, 3 over x minus 5 squared. Okay, I hope you found this video helpful.